Our next speaker is Justin Robinson from Georgia State University, talking about distance measurements for nearby AGN host galaxies.
Thank you so much. Let me go ahead and share my screen. Okay. Can everyone see me and hear me all right? Perfect. Thank you so much for the introduction. My name is Justin. I'm a grad student at Georgia State University, and I'd like to tell you a little bit about my work trying to measure distances to as many of the nearby AGN host galaxy family. So let's go ahead and get started. Here's one of the all-stars of the AGN host galaxy group. This is NGC 4593. And as I'm sure most of you may know, AGNs are unresolved point sources. And so we haven't been able to directly image any, but we think we have a pretty good idea as to what their structure is and what they're doing. So if we pretended that we could zoom all the way into the center, we would probably see something that looks like this. And I think we know the usual AGN diagram, but I like this one because it's a nice departure from the normal exploding donut that we've all seen. So the main components here, we have a supermassive black hole down there in the center. We have the accretion disk that's surrounding the black hole. And then surrounding this entire region, we have those thick photoionized clouds that are orbiting at Doppler velocities that broaden any emission lines that come from this region. And so that's the broad line region seen right there. And for the past 2 decades, as we've measured supermassive black hole mass in both active and inactive galaxies, what we've discovered is that black hole mass scales with certain large-scale galaxy characteristics. And 2 examples I've shown here, where black hole mass is on the y-axis, and the luminosity of the bulge is on the left, and then the stellar velocity dispersion of stars in the bulge is on the right. And this was a surprise when we discovered this because the size and dynamical scales are so vastly different here. The sphere of influence of the gravity of the black hole is orders of magnitude smaller than the size of the bulge. And so the general interpretation of these scaling relationships is that black holes and galaxies grow up together. They have a co-evolving relationship, or at some point in cosmic time, their evolution was connected. And so we're able to gain insight into black hole galaxy evolution over cosmic time by studying these scaling relationships. And so it's getting more and more important to make sure that the measurements that these relations rely on are as accurately measured as possible. For AGN host galaxies specifically, we have scaling relationships such as this, where the broadline region size scales with the luminosity of the AGN, or a brighter AGN will give you a larger broadline region size. One of the most important things about this scaling relationship is that all secondary black hole mass estimates in distant AGNs rely on this relation, where normally for nearby galaxies, you would have to directly measure the size of the broadline region, which takes a lot of monitoring time. So you can kind of shortcut that by just measuring the luminosity of the AGN, using this to predict the size of your broadline region, and then back out a black hole mass from there. The issue, though, is that the largest known uncertainty in this relation, and therefore the largest known uncertainty in any black hole mass estimates from this relation, is distance, because luminosity goes as the distance squared. So if you don't know your distance, your luminosity is off by, a lot squared. And that's because the vast majority of points in this diagram have distances that are measured only from redshift. And the issue with that is that when you measure a galaxy's distance using Hubble's law, you're assuming that all of the galaxy's recessional velocity is due to the expansion of the universe. And we know that's not true because gravity is a thing. Galaxies interact with each other through gravity, and so some component of their radial velocity that we measure is due to local gravitational interactions, and we call those peculiar velocities. And it's been able to be measured for the local group of galaxies around us by the Cosmic Flows program. It's a large compendium of tens of thousands of galaxy distances in the local group, and their velocities in supergalactic coordinates are plotted here. So this program has been able to measure the distances and therefore peculiar velocities of all of these galaxies. And so the red points here are the peculiar velocities going away from us and blue coming towards us. And if we just subtract off the expansion of the universe, what we're left with is the velocities of galaxies, only the velocities of galaxies that are induced by gravitational interactions. And so these are the peculiar velocity flow lines of the local group, our local supercluster, Laniakea. And so the larger a peculiar velocity a galaxy has, the more inaccurate a Hubble's law-based distance is going to be, and therefore any measurement that directly relies on distance, most importantly luminosity, is going to be inaccurate. So where I come in is, and where my group comes in, is we've tried to measure as many distances as possible to as many AGN hosts as possible to alleviate all of these issues. And because Most AGNs are hosted in spiral galaxies. We have been able to use the Tully-Fisher relation, which says that if you are able to measure the rotation rate of a spiral galaxy, that will predict its absolute magnitude or its intrinsic brightness. And the reason why this works is that the faster a spiral galaxy rotates, the more mass it has. And for galaxies, that means that more mass that's locked up in stars. So the more stars you have, the brighter that your galaxy is going to be. So to measure distances for all of these galaxies, we had to measure their rotation rates. And the way that we did that was we targeted all of these galaxies and their neutral hydrogen emitting at 21 centimeter wavelengths. Hydrogen is the most abundant element in the universe, and it's the most abundant element in spirals. Neutral hydrogen is also very cold, and it's dominated by rotation. And so it's a great thing to target if we want to measure the rotation rates of all these spiral galaxies. So in terms of a single emission line, if nothing was rotating, we would have a lot of flux centered at whatever the radial velocity of the galaxy is. But just like everything in the universe, this spiral galaxy is rotating, which means that one side of the disk looks like it's always coming towards me, and one side of the disk always looks like it's going away from me. So some of the flux in this emission line is going to be pushed to faster velocities, and some of it will be tugged to slower velocities. So this emission line will be split depending on how fast the galaxy is rotating. The faster it rotates, the farther apart these peaks are going to be. So in real life, we target an AGN host galaxy. We observe it with a single dish radio telescope. The Green Bank telescope was our telescope of choice. And then after a while, out pops a rotationally broadened emission line from neutral hydrogen. So all of the rotational information is contained in here. And so we've targeted 24 total galaxies using this method. And so we have 24 emission lines from neutral hydrogen and therefore 24 rotation rates. Now, the last thing that we need in order to measure distance is measure the galaxy's apparent magnitude, which we would compare to the absolute magnitude predicted by the Tully-Fisher relation and constrain distance that way. The issue, though, is that these are active galaxies. AGNs are extremely, extremely bright objects. They can sometimes outshine the total integrated light of their host galaxies. And so, the reason why the Tully-Fisher relation works is that it relies on stellar light in order to trace mass. So we needed to find a way to separate out the galaxy light from the AGN contamination. And the way that we did that was through surface brightness modeling of the optical and near infrared images of these galaxies using the GalFit software. So here's how that works. We have an original image, and what we're going to do is model the surface brightnesses of each morphological component separately. So for a spiral galaxy, that's a disk, that's a bar, that's a bulge, and an AGN in our case. So we'll start with a model of the disk and then track our progress by subtracting the model from the image in our residual over here. So you can see that just from the disk, we got rid of those giant wispy components, but there's a lot of unaccounted for light in the center. So let's throw in an AGN, let's throw in a bulge, and it doesn't seem to have helped us that much, probably because there's a giant bright bar there in the center. So let's throw in a model of a bar and see how we do. We're almost there. Looks like the only thing that we need left is that bar lens structure that's in the center of the bar. So let's throw in a bar lens and see how we do. And it looks like we captured most of that light. And so what I like to think of is that now we have a kind of Jenga set of all of the brightnesses of each morphological component constrained separately with the AGN sitting right on top. So the only thing that we need to do is flick off the AGN and then sum all of the other components to arrive at galaxy-only luminosities. And so we use those as our apparent magnitudes. We compare those to the absolute magnitudes predicted by Tully-Fisher and constrain distances that way. And for those of you who have used GalFit, if there are any here, you'll know what I'm about to say. For those that haven't, one of the more unique features of the software is that when it crashes, it's nice enough to print this out for you. So that's fun. What's also cool is that for the optical and near infrared images that we used to model the surface brightnesses and therefore model the galaxy only apparent magnitudes, we were able to image 4 galaxies with a 3.5 meter at Apache Point in BVRI filters. And here's an example of that process for NGC 2617 here on the top right. And then for some nearby galaxies, we were even able to use the 0.5 meter ArcSat for 2 galaxies, again in BVRI imaging. And here's an example of one of them, NGC 6814. And so there's 24 galaxies in our sample, and the telescopes at APO were able to give us the optical and near infrared images for a quarter of our sample, which is pretty cool. And so here are some of our results of all of our distances. For most of our sample, we were able to measure distances in 5 total bands. And we compare those not only to each other here, but to the distances that were predicted from some Hubble Space Telescope imaging that we were able to get. And thankfully, things look like they agree with each other, which is always nice. And then here is our Hubble diagram, where we have the galaxy's radial velocities plotted as a function of distances predicted by the Tully-Fisher relation. And then plotted, just for comparison, is the 2 constraints on the Hubble constant, which that's all I'll say, that's not my research. And the black dots are the certain Tully-Fisher distances, and the open dots are the uncertain ones. And there's a couple of ways that we went about choosing which is which. One of them was comparing our distances to the small handful of distances that have already been measured for these galaxies. There's only a couple of them through Cepheids and surface brightness fluctuations, which we show good agreement with. Thank you. The other way is that we again look to cosmic flows and look at their mass distribution of all the galaxies that they've mapped in the local group. And so here is their Hubble diagram with the Hubble constant in red. Each little cross is a small collection of galaxies. The bigger circles are clusters of galaxies. And all of these have distance measurements, which means that they have peculiar velocity constraints. And so the useful thing to us is that they were able to model the local peculiar velocity field depending on where you're looking in the sky. So for each one of these points, we were able to look at the mass distribution around each galaxy and compare our measured peculiar velocity to that that's expected in the region. And if things match up to what's expected, we say good. If it's highly deviant from any expected peculiar velocity, depending on how many galaxies there are available for the model, we say that those are uncertain. But at the end of the day, we were able to measure 13 certain distances to galaxies that had never had a distance measurement measured before. And then for the other handful of galaxies, we show good agreement with other distance ladder methods, such as Cepheids and surface brightness fluctuations. And that's all I have for you today. So I'll say thank you, and I'll be more than happy to take any questions.
Oh, thank you. Interesting talk. Mike? And Nancy.
Sorry.
We're clapping. We're not
Sorry,
raising
I was
hands.
just-
Thank you.
Okay. My largest question about this is, could you actually use this to talk about the distribution of dark matter in certain areas, as well as getting the distances?
Yes, that was the second half of my project that I didn't have time to talk about today. But we did combine their distances with their rotation rates and their physical sizes. That was the estimated size of the hydrogen distribution, and so we're able to backtrack out the total enclosed mass just by using the virial theorem. And my previous project that we did about 2 years ago, we were able to constrain the stellar and gas masses, and so we were able to separate out the baryonic content, the luminous matter, from the total gravitational matter. And we do have dark matter mass estimates for all of these galaxies.
That's very, very interesting, and should definitely post a link somewhere in the chat. So I'd like to read that paper.
Sure, absolutely.
Okay, I do have a question. May I, Joanne?
Yes.
Sorry, Justin, can you post that in the Slack channel as well so that we don't lose it?
Yeah, absolutely.
Nancy.
So Justin, remind me, so it was neat to see the use of both the 1/2 meter and the 3.5 meter. Can you remind me how many are there? And I think you said that you have already achieved measurements for a portion of your sample. I can't remember if it was half of your targets. And so are any of the others going to be achievable with ArcSat, or do you really need the 3.5 meter for the rest of them?
So the rest, the reason why we targeted them with the 3.5 and with ArcSat is because those are the ones that we didn't have imaging already in hand. So for the 3.5 and the 0.5 meter, the images for those made up a quarter of our sample. So 6 galaxies out of the 24 that were in our sample. So a very large portion and some very, very nice images. So we are appreciative for the time that we got on both telescopes.
Thank you. Great.
Thank you very much. And our next speaker is